Hello and welcome back to MathsBytes. This is video 6 in the binary number series, and we will talk about how to convert binary numbers to decimal numbers. We will use the binary place value table for these conversions, and I will show you a few examples. Then you will have a chance to do some practice questions. First, I would like us to remind ourselves what binary numbers are and how the binary place value table looks, as we will use this table for the conversion. Can you please spend a few minutes trying to write down a few binary numbers and draw out the binary place value table? Also, try to think about how you could describe binary numbers to someone who never heard about them. Here are a few examples of binary numbers. And here is the binary place value table. If you have written different examples on your piece of paper, that is fine, as long as you only used 1 and 0 in your numbers. I have also used the notation for binary numbers to be extra sure everyone is clear that these numbers are binary. It is not a problem if you didn't use the index notation. It was clear enough from the context that we are talking about binary numbers. Now, how would you describe what binary numbers are to someone who had never heard about them? Here's one way. Binary numbers are base 2 numbers using only the digits 1 and 0. Every place value in these numbers is an exponent of 2. I hope you have written something similar onto your paper. It doesn't have to be the same, but your description also has to capture the essence of the binary numbers. So if you have missed out one of the following concepts, base 2, using only the digits 1 and 0, or place values of exponents of 2, then you have to make sure you remember all of these one way or another. You could have used power or index instead of exponent. They all mean the same. As I mentioned in the previous video, using flashcards are a very useful way of helping you to learn important concepts. Try to use them and test yourself on the definitions, concepts regularly. Now, how could we use the knowledge of what binary numbers are and the binary place value table for decoding which decimal number is hiding behind a particular binary number? This is basically what we do when we are converting a binary number to a decimal number. We identify the decimal equivalent of the binary number in front of us. Let us try to find out which decimal number is the same as 10011. Well, if there was a way to identify which digit is associated with what place value, then we can do the same calculation we did with the decimal numbers in video 3. This is exactly the reason why we spent time on the decimal place value table and the binary place value table in previous videos. If you are unsure of what I am talking about, I suggest you watch those videos before continuing with this one. I'll leave the links in the description. So let us place 10011 into our binary place value table. When placing a binary number into the binary place value table, we need to make sure that the rightmost digit of the binary number goes into the unit place value, which is also the 2 to the 0 place value. Remember, when we looked at the place value tables, we always started with the rightmost column being the unit column. This way, even when we had different lengths of tables, the common columns always represented the same place values. So, once the number is placed into the place value table correctly, how could we find its overall value? Well, if you remember with the decimal numbers and the place values, we just multiplied every digit with its associated place value, which is the column heading we place the digits into. Actually, this is the exact method for converting any number into decimal. So how does it work with a binary example? We have a 1 in the place value of 2 to the 4 or 16, a 0 in the place value of 2 to the 3 or 8, another 0 in the place value of 2 to the 2 or 4, a 1 in the place value of 2 to the 1 or 2, and a 1 in the place value of 2 to the 0 or 1. The overall value of the binary number in decimal terms will be the sum of these place value and digit multiples. We can write this as follows: 1 times 2 to the 4 plus 0 times 2 to the 3 plus 0 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0, which is the same as 1 times 16 plus 0 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1 if we use the non-exponent version of the place values. Now, anything multiplied by 1 is just itself, and anything multiplied by 0 is 0, which means we can simplify the above to 16 plus 0 plus 0 plus 2 plus 1, which adds up to 19. So 10011 in binary is the same as 19 in decimal. One example is no example. So let us look at the following two binary numbers and find out their decimal equivalents. Let us place the first number into our binary place value table. We place the rightmost digit into the smallest place value in the table, which is the unit value. Then we fill up the table by copying the remaining digits of the number in a kind of backwards way, making sure we don't miss any of the digits. Again, looking at the digits and multiplying them with their place values, we get the following combination, which is the same as knowing that every number multiplied by 1 is itself, and every number multiplied by 0 is 0, we can simplify to 32 plus 8 plus 2 plus 1. Now, 32 and 8 makes 40, 2 and 1 makes 3. So 101011 in binary is equal to 43 in decimal. Whenever you use the equal sign to note the equivalence between a binary and a decimal number, you need to use the little 2 and 10 in the indexes, or what you write out will not be mathematically correct. After all, 101011 is not equal to 43 in general. Now, let us do the next example of 110110. Again, place this number into the binary place value table, starting with the rightmost digit in the units place. We get, using the digit and place value combination, again we get, which is the same as, and again, knowing the rules of multiplying by 0 and 1, we get 64 plus 32 plus 16 plus 4 plus 2. Now, this sum is not the easiest to do without a calculator if we do it in order. However, luckily for us, the order of addition is changeable. You can add numbers in whatever order you would like, and the answer will still be the same. Try out a few sums in your head. Don't just take my word for it. So, how about if we group this sum by pairs of numbers that are easier to add in our heads? 64 and 16 are numbers that add up to a multiple of 10, as 4 and 6 are one of the 10 number bonds. There are no other number bonds present, so the other three numbers we can keep in the same order to get the new sum of 64 plus 16 plus 32 plus 4 plus 2. 60 plus 10 makes 70, 4 plus 6 makes 10, so 64 and 16 makes 80. This way of adding, when you first add the tens and then the units, is called chunking and is very useful to do mental arithmetic. The rest of the numbers add up to 38. Now we just have to add together 80 and 38. 80 at 30 is 110, add 8 is 118. This means that 1110 in binary is equal to 118 in decimal. Of course, if you can use the calculator, none of this is necessary, but it is always good to have some skills in your disposal for making sure you haven't made a mistake with the calculator. Let us do two more examples for good measures, so you can observe the flow of the conversion and become more familiar with the process before it is your turn to try your hands on these conversions. If you feel you are ready to do the calculations, feel free to do the questions alongside me. Here are the numbers we will convert. This time, I will place them both into the place value table before I do the sums. Again, don't forget to start placing the rightmost digit to the unit place value and work from right to left. Here is the filled out place value table. Next, we will have to write out the sums for the numbers. I will start with the sum for 101001. The place value and digit multiples are, which is the same as, or simply, as the multiples of zeros don't contribute to the sum. Remembering our number bonds, we can add 16 and 4 together to 20 first, then add this to 64, which will give us 84. Then the last term in the sum is 1. So the decimal equivalent is 85. Finally, we can write the answer as 1010101. Binary is equal to 85 in decimal. Following the same principle for the last example we get, which is the same as, knowing that multiplying by 0 makes the number 0 and multiplying by 1 just gives us back the number. Now, this sum is somewhat more challenging, so let us first think about if we could match up some numbers that are easier to add together without a calculator. 128 and 2 nicely adds up to 130, so we have that with two numbers already. Then 64 and 16 are also a nice pair, adding up to 80. So far, 130 and 80 adds up to 210, and we still have to add on 32 and 1. 32 and 1 makes 33, which added to 210 will be 243 in total. So, 11110011 in binary is the same as 243 in decimal. Now I think you have been sitting on the sideline for long enough, and now you are hopefully very eager to get involved. Remember, maths is not a spectator sport. You have to try things out and often make mistakes to learn. So, here are a few binary numbers for you to try to convert them to decimal numbers. Pause the video here and do try these questions. Practice makes perfect. And here are the answers. Don't get disheartened if you have made a mistake. Rather, take this as a learning opportunity and try to find out where you went wrong. Did you make a mistake when writing out the place values? Did you copy down the place value to add together wrong? Or did you mess up the addition? If you know where you are likely to go wrong, you can start paying attention to those steps and correct for them. Remember, every one of us had to learn these things, and we have also made mistakes. It is all a natural part of learning. Now let us summarize what we learned in this video. We have learned that converting binary numbers to decimal numbers can be done using the binary place value table. First, we place the binary number into the table in a kind of backwards way, starting with placing the rightmost digit into the unit column. Then we multiply the individual digits with their place values and sum them up. If you cannot use the calculator, this summing up can get a little challenging, but by pairing numbers together that are simpler to add up, such as 16 and 4 or 32 and 8, we can make this process faster and less prone to mistake. Lastly, you should always write out your final answer using the standard notation for binary and decimal numbers. Now, throughout the video, I have written out both the index and the ordinary number versions of the place values, such as using both 2 cubed and 8. You might not need to do this in your class. You check with your lecturer teacher. However, I wanted to make sure you know both ways of doing the calculations, and I leave the decision to you whether you need to use both or just one of them. In an exam, I would recommend being as clear and as neat in your working out as possible. Your lecturer teacher will reward you with high marks for your effort. It can be quite disheartening to mark a messy work, and if your work is too messy, your lecturer teacher can easily misread what you have written. Anyway, I hope you have found this video useful, and you now feel confident in carrying out binary to decimal number conversions. In the next video, we will still be doing these calculations, but I will show you some shortcuts that can speed up the process, and we will come up with our own step-by-step instructions or algorithm for solving these questions. Until then, keep learning one byte at a time.